All right, let's try something a little bit different. We want to roll 2 dice 600 times, and we want to count the number of times I get a sum of 7. So let's look back at our chart. I wish I had that available for you to see, but you should have that chart available. Getting a 7 is actually the most likely. It happens 6 out of 36 times. So let's write down our x, n, and p. Okay, first of all, is this binomial? Absolutely. We're running identical trials n times. N in this case is 600. The thing that we're looking for is either success or failure. In this case, getting a 7. And the probability of getting a 7 is 6 out of 36. Oop, that's in the wrong spot. The probability of getting a 7 is 6 out of 36. And then the number of times that we're looking to get that probability of a 7 is exactly 54. So I'm looking for the probability of x being exactly 54. So I'm going to use my binomial distribution function, binom.dist x, comma n, comma p, comma false here because we want exactly, not cumulative. And that's a small number. Close to 0, pretty much 0. So this is, again, this is 0.000000216. So it's a very small number. It's basically 0. Okay, so it's very unlikely that this would happen. How do I know what a normal range of values would be? Like, how do I figure out what range of values would be normal? How many 7s should I get around when I roll 2 dice 600 times? Well, it turns out that it's very easy. We already calculated how to find the mean and the standard deviation of a regular discrete random variable distribution, probability distribution. That's what we did last time. And in the warm-up, we calculated the mean 2 different times. This binomial random variable is a specific instance of a discrete random variable, but it's just way easier to calculate the mean and standard deviation. Here are the formulas right here. To calculate the mean, all I need to know are the number of trials and the probability of success, and that gives me the mean. And to find the standard deviation, all I have to do is square root the number of trials times the probability of success times the probability of failure. So we need to calculate, if I wanted to know, like, what is a normal range of values? Like, how many times should I normally get 7? What's the average number if I did this experiment of rolling 2 dice 600 times and I did it 1,000 times? On average, how many 7s would I get? And so we need to, I need my x. I don't need my x to calculate the mean. I just need n, and I need p, and I need q. Okay, so n in this case is 600. I'm rolling the 2 dice 600 times. The probability that I roll a 7, we already calculated. That's 6 out of 36. And q is always 1 minus the probability of success. So that's going to be 0.8333. So if I wanted to calculate the mean, mu, the expected value for this probability distribution, that's going to be n times p. And I should expect to get about 100 out of the 600 times I should roll a 7, on average. So now let's find the standard deviation. I'm going to write out standard deviation because the symbol for sigma is not easy to call up. And let me move this out of the way. So this is going to be the square root, SQRT, of n times p times q. And so the standard deviation comes out to 9.1287. Now, in the first one, I said 54. And you might say, well, 100 and 54, not that far apart when we're thinking about 600. But remember, and this is important, for n greater than 30, binomial distribution is normal. And what also has to be true is p can't be that close to 0 or 1. But really, we want n to be bigger than 30. And so if the binomial distribution is normal, then we can use something called the empirical rule. And remember, the empirical rule says that 99.7% of our data values are within 3 standard deviations of the mean. And so let's just make sure that we're within 3 standard deviations of the mean. So I'm going to find mu, oops, I'm not going to do that. I'm going to find mu minus 3 times the standard deviation. Let's call it sigma. And I'm going to find mu plus 3 times the standard deviation sigma. And that'll give me a nice range of values. So I'm going to find the mean, and I'm going to subtract 3 times the standard deviation. So that brings me at about 72, 73. And if I do the mean plus 3 times the standard deviation, that brings me to 127. Okay. So 54 was outside of that range, which is why our probability was so small. It is very unlikely, 99.7% of the time, we will fall between 73 and 127. So that would be a reasonable range. If I could add a part D here, if I got a sum of 7 200 times, would I be surprised? And the answer is absolutely. This is very much outside the high end of what we would expect to be reasonable. Now, does that mean it could never happen? No. Of course it could happen. I could roll a sum of a 7 200 times. And in the history of the world, it might be the only time it ever happens. But it's not impossible. I can do it. But I would be so surprised. It'd be like sitting a monkey in front of a keyboard and having them just randomly type out the text Moby Dick. Given enough time, it could happen, but I would be very surprised. All right. So in the next video, we're going to do another example just to solidify all of this and hopefully put it all together.